Yes, I think so. Do you hear me? So thank you very much for the introduction and in particular for the invitation here. And Joshua, to you, thank you in particular for all the emails. I remember last year when these difficult times were, and you answered every line of every email I wrote. So thank you very much. It was very helpful.
Thank you for coming.
As was mentioned, I will speak about a coupling approach, an approach to realize a PT-symmetric quantum system, in particular for Bose-Einstein condensates. So let me give an outline of this talk. First, the first part of the talk I will give is, for most of you, I think, just a reminder, because I spoke many times about PT-symmetric Bose-Einstein condensates, these PT-symmetric nonlinear systems. But I will need every part of this as to understand what happens here when we try to realize these in and outflux of atoms for this Bose-Einstein condensate. What here is modeled by a PT-symmetric complex potential with a coupling to different Bose-Einstein condensate wave functions. So let us go to the first part. A short reminder, I think this is known to everyone. We saw it also at this conference many times. We have the operators P and T, which act like this. And then if you want to speak of a PT-symmetric quantum system, we speak of a system of which the Hamiltonian commutes with the combined action of the P and T operator. In position space, and all analysis I will do is in position space. We can calculate this explicitly, and this will lead us to this well-known condition for the potential, that the potential at position minus x must be the complex conjugate of the potential at position x. So that's what we work with, and I directly want to go to the quantum system we want to investigate, and this was already mentioned, proposed in the outlook at the last lines of a paper by Kleiman and co-workers written in 2008, and the suggestion they had was that we can have a Bose-Einstein condensate, put it in a double well structure that is in a trap which has these two wells here. We, in our calculations, implemented this by having some harmonic trap, and in one direction this Gaussian barrier which divides it such that we get this double well structure, and then implement the positive and imaginary parts which effectively describe an influx and outflux of the probability amplitude, or for the Bose-Einstein condensate, an influx and outflux of atoms by an imaginary potential. We took this shape here, which was due to our calculations, but the explicit shape doesn't matter. The important thing is that it is an antisymmetric imaginary potential, and in this case it describes here a positive imaginary part, or an influx of atoms on the right side, and on the left side outflux of the atoms. And what then has to be considered also in these Bose-Einstein condensates is that we want to add atoms to the condensed phase, so everything has to happen in a coherent way, and I will talk later about this, how we could implement this. So we do all this analysis on the level of the mean field approximation, so on the level of the Gross-Believsky equation. We could show in some publications that also this can be shown on the single particle level, that this mean field limit can well describe the influx and outflux of atoms we want to have. If we introduce it, we do it in some special system of units, such that we end up with a Gross-Believsky equation in this dimensionless form. This brings us already to a first question we can ask, because if we always speak about PT-symmetric quantum systems, we speak about linear systems, and here it is clear if the potential I showed fulfills this condition, it is PT-symmetric. In these nonlinear equations, we can ask an additional question, because we have here this nonlinear part, and obviously we can consider this to belong to the real part of the potential, because everything here is real. And this tells us that the solution we find, the wave function, will have an influence on the PT-symmetry of the system at all, because if this has to be a symmetric function of x, otherwise it will not be a PT-symmetric system, or if we consider it to be part of the Hamiltonian, it will not be a PT-symmetric Hamiltonian. Let us go directly to the results, because I think many things of this are well known. we have the typical structure. Let us first switch off the nonlinearity. So look at G equal to 0, the typical structure of a PT-symmetric system. We look only at the ground state and the first excited state, because in this system, in the energy region we are interested in, only these are, and for the potential strength we use, only these two states are affected significantly by the imaginary potential. And we see the typical structure. We have two real eigenvalue solutions for some low values of the non-hermiticity parameter, or the in and out coupling parameter gamma here, and they move together, and at some point we have this exceptional point where they merge and coalesce, and beyond this exceptional point we have two solutions with complex conjugate eigenvalues. Let us go to the system with nonlinearity and look directly here at the blue line, which is already a strong nonlinearity here, 0.2. And we see the structure changes somehow. We still have these two real eigenvalue solutions. Here are the imaginary parts, which are still at 0. They coalesce again at some point, but here nothing happens. No new states appear. They appear already here. They bifurcate. So that's the more complicated structure we talked about in the discussion of the last talk. They bifurcate from one of these real eigenvalue solutions here. This is the ground state, and truly form two complex conjugate here, positive and imaginary part solutions. This can be brought to the very extreme case where they never bifurcate from one of these states, but exist from the beginning and end up in the well-known self-trapping non-symmetric states of Bose-Einstein condensates in such double well structures. So that are the observations we can do here. But now let us look, is this still in this nonlinear system connected to PT-symmetry? Of course it is. This is already well known now. If we look at the wave functions for the real eigenvalue solutions, this here is for the ground state, we find that we have a symmetric real part. We can choose the global phase such that it is like this, and the imaginary part is antisymmetric. This ends up with a square modulus of the wave function, which is also a symmetric function of x. So this is a PT-symmetric wave function and renders also the Hamiltonian PT-symmetric. The same can be found for the excited state, for the other real solution, where we have again the same structure, and in particular a square modulus, which is a symmetric function of x. This situation changes for the solution with complex eigenvalues. Here we have a completely different structure. We have wave functions which have no special symmetry, so also no special symmetry of the square modulus. The same is true for the other state, and this shows in this case, if we consider this nonlinearity to belong to the Hamiltonian, also the PT-symmetry of the Hamiltonian is destroyed in this case, so we have no PT-symmetry at all, or only of the linear potential, which of course remains in the system. So these are the states we can find here. There's, of course, always, if we want to have this to be observable, the critical questions, will these states be observable? And for this, they have to be dynamically stable. The first step to investigate whether they are dynamically stable such that some small fluctuations don't change them too much, such that everything gets lost, is to look at the so-called Bogoliubov-Duchenne equations. This means we start here with some wave function, which is composed of one stationary state, one of these real eigenvalue solutions we found so far, the ground state or the excited state, and we add a fluctuation of this form given by these coefficients u and v, and a small coefficient delta, which describes the strength of this fluctuation, and we assume this to be small. Then we put this into the Gross-Bielewski equation and linearize with respect to this coefficient delta. This then leads us to the linearized Bogoliubov-Duchenne equations, which we have here for these coefficients u and v, and in particular tells us about the stability via this parameter lambda here, because we see in this time evolution ansatz here that for real values we get growing or decaying solutions, and due to the symmetry we will always have both signs. So if we have some real contribution, we will always have a growing contribution of the instability or the fluctuation, which then is unstable and renders the whole system unstable. Or we can have purely imaginary solutions, which then will just give us some oscillations around these stationary states, and they will be considered to be stable. So let us look at the solutions we find here for the grounds. Let us look first at the excited state. That's the lower panel because that's the more boring one. We find that all eigenvalues, as long as this state exists, are purely imaginary. So that's the case we consider to be stable. So the excited state is stable until approximately it vanishes. This is not exactly the point where it vanishes. There is a small shift, which is also well known or understood already, because we know that the Gross-Pedievsky equation is not norm depends on the norm of the wave function. We then can look at the ground state, which is more interesting. We see that again for small values of the non-hermiticity parameter, we have here these solutions where these states show a stable behavior, so imaginary eigenvalues, but at some point they change to real eigenvalues, showing that this condensate is unstable. And if we compare these points, this approximately appears where we have this bifurcation of these complex eigenvalue solutions, these PT broken states, which obviously induce some instability to the whole system, also to these stationary states. And I think this can also be understood well. There will be some fluctuations which go into these states and will end up with these growing modes and destroy the whole condensate. So that can be found here. We can also look at the stability via the complete dynamics, so integrating the time-dependent wave function with the time-dependent Gross-Pedievsky equation, and we do it always with a superposition of these two states, these two stationary states, ground state and the excited state, and we modify the phase relation sometimes between them. And the typical structure we get is if we switch off the non-hermiticity parameter, so we have no in and out coupling of the atoms, we have this typical structure if we only include two states of these oscillations between the two wells. So this is here the x-axis, and these dots here show us, these bright show us a high probability amplitude, so the condensate is mainly in one well, and we have this oscillation with a phase shift of 90 degrees. This changes a bit if we include some gamma values, so some in and out flux of the atoms. We see two effects on this. The first effect is that the frequency changes, and the second effect is that also the phase relation changes. One can see already here that there are some regions where when we integrate over the whole trap, we will have some lower probability amplitude or higher probability amplitude, so a lower or higher number of atoms in the total system, which is of course possibly due to these effects with gain and loss. The very extreme case is if we go close to the exceptional point, close to the point where the two real eigenvalue solutions vanish. Then it is known also for linear systems that this frequency of this oscillation goes to infinity, it diverges, and we also observe that this phase shift becomes more pronounced. So here clearly we have almost no atoms in the whole system. Here we have a large number of atoms in the whole system. But this oscillation still seems to be stable, even in a region where we could see that one of these states showed in the Bogoliubov-Deschênes equations that it is unstable. And the important thing about this is that with which phase relation we start our system. Because if we start for a significantly lower value of gamma, where these complex eigenvalue solutions exist but are far should not be have the same effect as here. In particular, here the two real eigenvalue solutions are far away from the point where they stop to exist, but start with a different phase relation. We observe here, even if although we start in the completely with the atoms in the system, or almost completely with the atoms in the well with loss, that we have some influence here or some tunneling effect to the well with gain, and the whole system explodes. And we investigated it further, and now it is understood that this happens always, or can happen when we have an increase of the probability amplitude at the beginning of the dynamics. And I think it can be understood better with this phase diagram, which I want to use to summarize the results we obtained so far here in the system with a complex potential. We saw that we have our parameter gamma defining the outflux of the atoms. We have our parameter g, which defines the strength of the nonlinearity, or you can consider this also to be a parameter defining the number of atoms, because you can always shift the strength of this g into the number of atoms, because it appears in this nonlinear part multiplied with psi squared. So you can always normalize psi to unity and shift all the number of atoms then into this g. We have here this region in which we only have PT-symmetric states, because, and here for g equal to 0, the typical case, symmetry breaking at the exceptional point, and the PT broken states appear. We also have the case of the coexistence of both states. So we have the states bifurcating from one of these solutions here, and this gives us this line, and we have some coexistence which becomes for larger g's, larger and larger here, until these real eigenvalue solutions vanish. If we now go back to the dynamics and try to understand why we can have this instability even at points where we don't expect it, we can see that we start maybe somewhere here at some value of gamma, and the number of atoms might increase due to this oscillation, and then we can cross maybe here this line, and this always can introduce this instability into the system, and this is what can then be observed. So the dynamics cannot fully explained by the Bouguereau-Dechaine equation or the stability of these states. It also depends on the initial conditions and is due to the combined action of this gain and loss effect together with the nonlinearity. So that was the summary of what we found in the complex potential solutions. I now want to go to study how we can find a possibility to implement these in and outflux of the atoms in such a way that it is consistent with that described by the complex potentials in a coupling approach. That's a question?
Could you go back to the so I guess I'm trying to understand the language. You start with only two states, right? Ground state and first excited
Yeah.
state. And so if both have real eigenvalues, that's PT-symmetric.
Yes?
And if because they come together, both become complex, then it is PT broken.
Yes?
So what is both solutions exactly? What does it mean? That the green part.
Okay. It's not only that, you can see it here, only in the linear system, they emerge exactly at the point where the other two solutions, the real eigenvalue solutions, vanish. And as soon as we have this nonlinearity in effect, we have already here these complex eigenvalue solutions which bifurcate from one of these states. And they are basically those states which in the linear system bifurcate here and appear. So the green region is just this region here between this point where the complex eigenvalue solutions appear and this point where the real eigenvalue solutions vanish. So is that the question?
Yeah.
Okay. Okay, I want to do this now in a coupling approach, but before I want to go to this, I want to mention some words about another approach we proposed 3 years ago. This consists again of considering a double well structure. So we have our double well, and we assume that we have some in and out coupling of atoms described by imaginary potentials. And one idea to implement this is to go to a four well structure. Here we have four wells, and we always consider the inner two wells to be our PT-symmetric system. So this here is the inner two wells here in the system. Then we assume that we have two outer wells, here one well and here one well, and that we are able to shift the energy levels of these outer wells. So we can shift one up and we can shift one down, and we assume that we can do this time dependently. And if we do this time dependent,
in this initial preparation,
yes,
you have disconnected condensates.
no, no.
Well, or it's a coherent.
We have an overlap of the wave functions. They are not, the potential heights are not such that they are completely separated. It's basically one condensate you can look at.
Because, well, it depends on the depth of this well.
Yes.
You can have a mod transition.
Yes, you can have, but we didn't assume this, and we didn't consider this case. So,
you are now, it's one coherent
Yes.
condensate.
yes, this is one coherent condensate, and it was, and we showed and calculated that it can be prepared in this manner. And then we start to move these potential heights here, so this up and this down, and this will give a net influx here from the atoms of this well to this well, and we can have here a net outflux from this well to this well. And if we choose a proper time frame to do this and a proper time-dependent potential, it was able to show that this can made be such that it implements a potential or the same effect as an imaginary potential with constant imaginary potential contributions. So these I gamma and minus I gamma contributions we had here so far.
But if it's one coherent condensate, then
Yes.
the number of particles in each well is not defined. You either define the phase, the coherence,
Okay.
or you define number of particles. So you cannot now
Okay. Then
definite number
that-
of particles go from.
okay, then you have to stop this at some point, this experiment, and give up the coherence for a measurement of the number of the particles. But if you start with this normalized wave function and look for the probability amplitudes, which will restrict to this inner well, you can find that the probability amplitude in this inner two system stays constant. And this here decreases and this here increases. So this is possible. Now I want to go to another idea which is more challenging, I think, but it has some interesting aspects to study, and this is what I want to do now. The idea is now that we again have a double well, and that we somewhere have some reservoir of atoms, and have an active outcoupling here from this reservoir and incoupling into our double well structure, an active outcoupling here and incoupling to our reservoir. It's not necessarily given that we have here some reservoir. I will not assume this in the calculations. I will just assume that we have here some influx which we in some way have under control, and here have some outflux which we also have in some way under control. A possible idea for realization might be, it was shown that from these wells atoms can be extracted by scattering with light waves, with Bragg beams, and it was also shown that these scattered atoms from the condensate fraction could also be again later brought to overlap. So it was shown that the coherent character still is present, and that it gives some fringes, for example, in interference experiments. So in principle, it should be possible to, with such a procedure, give some active coupling, some active driving of the atoms in such a manner. But as I said, I will not look further at this. I will only look at some incoupling and outcoupling of the wave functions. All what I will present now is on a very basic level. It's a first step, and so far we did not more than this first step, but it turned out to show some interesting properties I want to present here. I want to do it, as I said, as a first step in a very, very simple manner. I want to do it one-dimensional, and I want to use the simplest potential we looked at so far. This is a double delta potential. So we assume that our width of these two wells shrinks to infinitely small values. We have one attractive delta function for which models one of our potential wells. We have a second delta trap here modeling the second well of our double well setup. Then we assume that we here have, and we calculated this some years ago, these wave functions in the double well system, and we assume that we have some incoming wave function, and we assume that we have some outgoing wave function, and all this should be considered to give us here the system with these red lines. So that's the idea of the system, of the setup I want to use now. We use the dimensionless one-dimensional Gross-Pideevsky equation in this form with this potential here. That's the complex potential we use with these gamma values at the delta functions. So at x is equal to plus a, we will have the incoupling effect, a positive imaginary potential. Here we have a negative imaginary potential in the left well. And as before, in all calculations, I will assume an attractive contact interaction with these equations we use here is a positive value. I will use a fixed distance of the traps. I did not change it here in these calculations. And the wave functions are assumed to couple only in the trap, which means basically we have in one direction our trap and assume that these ingoing waves are coming from another direction, so that only in the trap we will have this overlap.
Different signs, plus and minus simultaneously.
Yeah.
It's still in front of the last plus and minus here.
Oh, this is only a minus. Excuse me. This plus is a mistake. So the eigenvalue spectrum, not surprising, is not very different from that I showed you for this double well spatially extended system. So in the linear case, two real eigenvalue solutions, exception point, the complex eigenvalue solutions. Here, the real eigenvalue solutions given with their stability here with this dashed line, the bifurcation where we have, or a third order exception point, where we have the appearance of these complex eigenvalue solutions, and here this point where these two real eigenvalues merge. So the aim is now to implement exactly these states, so the wave functions we have for the system and these energy eigenvalues, by substituting the imaginary contributions to the potential with some coupling effects to these wave functions psi2 and psi3. So that's what we want to do here. So let's first look at the coupling in one point. What do we have to consider if we want to replace this by an imaginary potential, or the other way around, replace an imaginary potential by this coupling? So we start with the Gross-Pideevsky equation for the first wave function, here only with the real part of the potential. Here we have now the coupling, some overlap with the wave function psi2, which gives us this in and out coupling defined by a coupling parameter eta, just giving us the strength. We assume it to be real and put later all phase relations in the wave functions, in the relative phases of the wave functions. We have the Gross-Pideevsky equation for the second system, again here with this delta trap, which it fields. And we have, again, a coupling, and this time it's a coupling to wave function psi1. The desired behavior now is that we can substitute this exactly such that it looks like this. Then we can calculate a bit, which is just bringing this psi1 to the other side, and now split it into the modulus part, here the moduli of the two wave functions, and the phase relations phi. These small phi are always the phases of the wave functions, are given here explicitly. If you want this to be real and put all phase information in the wave function, of course, if we have some other values here, We'll just change some values here, but let's work with one restriction, which will simplify our discussion. This tells us we need some phase relation to implement exactly this imaginary potential here. And also we have some restriction on the strength here, which will be given by the moduli of the wave functions. So that's basically what we can calculate here. We can now calculate the flux because if we look at the condition for the coupling in one direction, we can completely define via this equation either this gamma or eta, depends on which we want to give and which we want to calculate from the other. And then it turns out that the coupling in the other direction looks a bit more complicated. So for the second wave function, where we want to substitute here this eta psi 1, we have an expression here which looks a bit more complicated. And one can ask now, is this coupling asymmetric? Because the equations are so asymmetric. But it is not. What is important for us is that the outflux from one wave function is, of course, the influx to the other wave function. And, of course, this is fulfilled. We can calculate it if we use this representation here with these imaginary potentials and assume the continuity equation for in the presence of these complex potentials where we have these source and drain terms given by the imaginary potential. And this ends up here in this in and outflux to these two wave functions, here to wave function 1, here to wave function 2. And as we see, they are of the same strength, but of opposite sign. So we can really, with this condition here that we want to replace the imaginary potentials, get to a case where we have an influx from one wave function. The other wave function feels an imaginary potential of the same strength but opposite sign, so an outflux to this other wave function. That's for the coupling. So let's go back to the approach we want to take. We want to look here at the system where we have this wave function, the stationary state, influx of one wave function which I want to call psi 2, outflux to another wave function which I want to call psi 3. So that's the case we want to look at. Here these delta traps. So we have bound state, two in and outcoming state wave functions which are considered to be unbound and couple in the trap to this condensate, which was in our previous calculations the solution in a complex PT-symmetric potential. So let's look at the equations. They look, of course, a bit more complicated. We have, again, we start with the Gross-Pedievsky equation for wave function psi 1. Here now it feels both wells, the right well and the left well, with only the real part of the potential. And we have a coupling in the right well to wave function psi 2, a coupling to a wave function psi 3 in the left well. We have the Gross-Pedievsky equation for wave function psi 2. Its coupling, it's coupled only in one well to the wave function psi 1 in the right well, and the wave function psi 3, its Gross-Pedievsky equation, and its coupling to the wave function psi 1 in the left well. That's what I want to look at. We had this condition in one delta well. If we want to look at both, we have both conditions for both delta wells, and they look very similar, and they are also completely independent because we have here only wave function psi 2 and here only wave function psi 3. So if it turned out to work in the case where we only couple two wave functions in one delta well, we do nothing else here, but in two wells, two different wave functions, it should also turn out, and this is what the calculation gives, turn out to work, and it gives is given in the wave function. We have the two requirements at the two positions. We have two phase conditions, which are here, of course, opposite in sign, because we want to implement opposite signs of this imaginary potential, and basically this should be possible to fulfill, so there should be no problem. how can we find exactly these states? We want to show that we really can find them and that they exist, and later I want to show that they are also stable and this situation can be implemented here. So the idea is now to start with the solution in the complex potential. So this, our psi1, as I said before, we want to have exactly a representation of this psi1 we have in this complex potential. So this was exactly, is what we want. So we start with this wave function, and this is here given in the center picture. This defines what we want to have. And then we start with the same procedure to both of these unbound waves, so the upper one and the lower one. And the idea is we start with here a decaying solution, because we want to propagate it only to one direction, or coming in only from one direction, and propagate back in one direction. So we start here with some decaying solution in one side of the trap. Then we have this requirement of the amplitude and phase, which we here need to fulfill. And basically then we have to integrate further the unbound part of this wave function. But let's first discuss, do these decaying parts on one side really make sense? Is it reasonable to work with these wave functions? So of course for the outgoing wave I think this is clear and reasonable. We want to scatter the atoms in one direction, so in the other directions we should not have a probability amplitude of this condensate, of this unbound part of the condensate wave function. So I think this is reasonable to assume that this appears. For the incoming wave, this means that we have a total incoupling, so that all of this flux directly couples into the bound wave function. Of course, this is not necessarily fulfilled, and I think it also will be extremely hard to do so, but it simplifies here the calculations, and basically the effect is we need some amplitude here to fulfill all the conditions, and this amplitude can also be achieved by coming in with a larger amplitude if the incoupling is not perfect. So let's, for this calculation, to simplify it, assume that we also have here this decaying part, so that the influx or the incoupling to the bound state solution is perfect, or almost perfect. So the unbound wave function, if we want to look at the decaying part, it can be found in a very simple way. That's the well-known bright soliton solution. So this function here, which we can shift here with this parameter x tilde, that's a freedom we have. And important is that the phase relation at the coupling points is constant. We need, of course, to have the same chemical potential as has the bound state. So then the task is to find this bright soliton wave, or calculate it. It is found. This function is known. And then it has to be shifted such that here we have exactly the amplitude we need to get the correct in and out coupling effects. So we shift it via this parameter x tilde such that our conditions here are fulfilled. And this also determines the derivative of the wave function, so the complete decaying part of this unbound wave function is determined. It's perfectly determined. It's clear which wave function we need. There's no freedom of choice if we want to have to fulfill exactly this condition or implement exactly this imaginary potential we want to have. Then it's just implementing the effect of the delta potential to the wave function. So we have here this discontinuity in the first derivative, and then it's just an integration of this wave function here to the right, which can be done with an ordinary differential integrator because everything is one-dimensional. That's very simple. So basic fact is we have to find this bound part, and then everything else is defined, and then our whole wave function psi2 is defined and given, and the same obviously can be done for this third wave function. So there's nothing different. We can calculate it exactly the same way and have then this wave function of this second unbound wave. Of course, this was in this way simple to find these solutions, but again the question is this whole situation dynamically stable? And we looked at this directly in a full integration of the dynamics, because it was hard to find any information on another way on these unbound wave functions. Of course, of the bound states, we know whether they are stable or not, but the critical part is these unbound wave functions. So we did a propagation, a fully numerical one, and we did it with a split operator method. So we applied some time propagation of the wave function where we split the Hamiltonian into its momentum part, potential part, and switch between these representations via Fourier transforms. And we can see that this has to be done on very large grid sizes. So we took these wave functions, put them on a grid, and then propagated it in time with these equations. The number of the grid points is so large because we want to avoid boundary effects. So we have to be far away with boundaries from our inner setup where we have our double delta structure. And we also need a high spatial resolution because we have a delta potential. And here it turned out that the delta potential is very often very simple to use to get simple equations to help with some analytical insight. But if we want to do this exact propagation in time, it's very hard to do so because the singularity of the delta potential is hard to implement in some numerical methods for the time propagation. But we were able to do so and to calculate some reasonable results. So stable solutions are, of course, those for which we have fluctuations which are damped such that they vanish after some time. Unstable solutions are those for which these perturbations grow. And we found that this is more likely for large values of gamma. Of course, this is also known already from the stationary solutions in the complex potential. So let us look at a system. We started with this stationary ground state in the complex potential solution, and this is its time propagation. Again, here we have the time axis. Here we have the x-axis. So these points are where we have these delta functions. And we see, obviously, the probability amplitude is not constant in these delta traps. So it's not a true stationary state, which we found in the numerics to be realized. But it is a stably oscillating state. Of course, here it seems to get some perturbations. And if we look here at the incoming wave, here the white line is the point where we have the delta function. We see also that with increasing time, we have some perturbations which slowly approach our delta functions, but we could show that they all appear far from the trap and are basically related to the boundary we have in our system, so maybe this can be damped out. So we looked at this. And another effect which also brought some instabilities here to the system is the singularity of the delta trap. It is more stable or stationary for the case of the stationary excited state. So here we started the integration with the stationary excited state of the complex potential, calculated again the required unbound wave functions, and did the time propagation. Here again, the white lines indicate where we have these delta traps of the outer wave functions. It is somehow stable and stationary for some time, but again we have some perturbations which eventually destroy our condensate here, but all they again appear due to the singularity of the delta potential or at the boundaries. So in total we find that there are some solutions which are sufficiently stable, I can call it. We checked it by increasing, for example, the lattice size and saw that these perturbations vanish then or go to later times. And as I said, it's also part of the singular character of the delta potential. So maybe it's a good idea to do this also with some spatial resolution of the traps, which will simplify the numerics here in the time propagation, but give also some other points we have to think about. I want to add a further question, namely, so far we had two independent waves. The question now, of course, this is more challenging to use only one wave function which provides both influx and outflux to the trapped condensate. But for curiosity, let us ask whether this is possible. I just want to ask, is in principle the system able to support such states? So let's do this and calculate what we can do here and what we can calculate. So we have two Gross-Believsky equations. Here, this should, again, psi1 always be our bound state. It is now coupled at 2 points to one wave function psi2. The same for wave function psi2. It's Gross-Believsky equation, which feels the real potential here and is coupled at 2 points to our wave function psi1. The requirements we have now for the coupling are the same as before, but with the additional restriction that we don't have a wave function psi3 here, but a wave function psi2, and this somehow looks simpler, but of course gives some more restrictions to what we find. If we now know that use the known symmetry that we have a stationary PT-symmetric state psi1, we want to use this. This results in two conditions. One, that also the amplitudes of the wave function psi2 have to be the same at positions minus a and plus a, and that the phase relations at these points for wave function psi2 is the same as the phase relation for wave function psi1 at these points, plus pi, and this is plus pi is due to the fact that here we want to implement exactly these imaginary potentials. That's the restriction we have. Let's again start the stationary state with the stationary state in the complex potential. So we start with this wave function and search for the conditions which we have to fulfilled here in the traps to give the correct coupling. And then it's the same way. We can integrate just the outgoing parts. It's easy to fulfill this norm condition because this just, or modulus condition, because this just tells us we need some symmetric state, at least here in the inner part, which can be found easily. But more complicated is to fulfill the phase condition. For this, we required a numerical search which wave functions do fulfill this. But it is possible to find them. Here's an example. The red line is the probability amplitude for the stationary state. Here it's a symmetric ground state, for example, of the complex potential, which we implement now with this blue dashed line, which is the wave function psi2, providing the correct in and out coupling effects here. This calculation is now a numerical calculation for propagation of exactly this initial condition, not exactly of this. This is one condition where we started with the excited state of the complex potential system, and we find that we have a rather constant probability amplitude here, so a rather stationary state in the trap, and also some stable propagation of the waves outside the trap. So this is the unbound state providing these in and out coupling effects. So, but here I have to say it was only able in the time propagation to get some stationary solution for the excited state, for the ground state of the complex potential system. This was very early unstable. Even more challenging task is to require now, and this is also only for curiosity, that the wave function psi2 is also a bound state. So can we have two bound states of this double delta system by coupling them, which support each other, these imaginary potential contributions, or these in and out flux? So one wave function gives here an outflux, the other gets here the influx, and the other way round. So again, this is our system of the Gross-Believsky equations. Possible states are limited. This can be seen very easily. For a true stationary solution, we again require that the chemical potentials of them are the same. They have to be, otherwise we don't have this constant phase relation, which gives us a constant in and out coupling. We know that these states are non-degenerate, and this offers two possibilities, namely that the states are the same up to a phase shift, which is always allowed, or are switched around. So the one is the negative, the mirrored one of the other. So parity operator acted on the other. And for a correct coupling, of course, we need that for one wave function feels a positive imaginary potential where the other feels a negative imaginary potential. So in and out coupling must be vice versa. So there's only one choice, we have to use this. And thus, this all again gives us some condition on the amplitudes here and gives us some condition on the phase in which this angle theta appears. This is again this phase condition we have. If we now also consider that both states are PT-symmetric, we have to add this relation here, which is just the phase condition for PT-symmetric states. And then it turns out that we have a very restrictive condition on the phases, namely that the phase of these both wave functions at positions a and minus a have to be the same in modulus and have to be pi over 4. Only these states are acceptable. This is very restrictive, and one can ask, do these states exist? And they exist, and I want to show it in the stability diagram I had before. So we again here have our parameter gamma describing the in and out flux. Here we have our parameter g describing the nonlinearity. Here we have this case where we have only these bound states or these stable states, these real eigenvalue solutions. Here we have these complex eigenvalue solutions where one of these states becomes unstable. And the states which have fulfill the phase conditions are all situated on this blue line. And here one can see that it is also in theory very challenging to have such a situation, because only in this narrow range we have the possibility to have exactly this situation with some stable states, but also this was not stable enough to show in our numerical time propagations some stable resolution. But if one wants to find this, I think one can do so by changing some parameters of the potential, so the distance of the traps or maybe the real part of the potential of these traps. This offers some freedom to search here for better states if one really wants to. But in principle, it shows there are such solutions which can fulfill this. So in conclusion, we looked at PT-symmetric eigenfunctions which exist in these nonlinear quantum systems and are in wide ranges of the parameters sufficiently stable. We showed also that these solutions which can appear in these imaginary or with these imaginary potentials in a coupling or can be implemented by a coupling to further condensate waves or by this 4-well setup maybe. One can use 2 or more unbound waves to couple to them, and it could also be shown that there is some stability in the system, and basically all instabilities we found are responsible for this are these delta potentials mainly we used. So in particular it's singular character. And in principle also this coupling of 2 bound waves which support each other, this in and out flux, is possible. So the possible outlook is, of course, we can look at further parameters to find better and stable solutions. What is, I think, important is to go to spatially extended condensates. Of course, also to more realistic cases, 3-dimensional potentials, additional geometries. Atom laser setups are very interesting for this case, and the investigation of the in and out coupling process is also done by a PhD student of us in a microscopic situation. So thank you very much.
First, a small comment that probably it may be more natural to realize sort of the setting where you need the gain and loss, not in the atomic condensate, but rather in condensate of excitons polaritons, generally. But okay, that's a philosophical comment. A more particular one is about your model with the 2 delta functions, because obviously you may consider the limit when the distance between the 2 delta functions is vanishing. Simultaneously, of course, your coefficient capital gamma in front of the imaginary part must grow, so that the product remains constant, and then eventually you have a single singular point at which the real potential is simply a delta function, and the imaginary one is a derivative of the delta function, delta prime.
Yes.
It's a limit case of yours. So this model was considered before both trapped states and the scattering of incoming pulses on this pattern. These things were considered before. And some results roughly seem similar to yours. For example, you mentioned that the instability of the trapped states is chiefly determined by the singularity of the delta function.
Yes.
So in that case, which was called PT dipole, conclusion was more or less similar. So I'm wondering if you had a chance to compare in some detail your results with the previous results which were obtained for this PT dipole.
I have to look into these PT dipole results,
It was published a couple of years ago.
but I think it will be interesting at least to do so. It will, and we will do so.
Okay, I can give you reference.
Okay, I'm interested in this. Okay.
Yes. You are feeding particles in one well, and the other well is leaking particles.
Yes.
Is the arrangement. Now, is it not possible instead to organize things in such a way that that the ground state is getting particles, whereas the first excited state is leaking?
But both states need to get particles and to have a loss of particles. Yes. Otherwise,
So this can be done, but probably if you upgrade the
and also to have this coupling constant, we need two states with the same chemical potential. So I see a problem that this coupling will be constant in time, because the ground and excited states, of course, have different chemical potentials.
But in fact, this setting is known, it's called LASIK.
Yes.
Essentially, this is LASIK.
Yes, that's
No, not PT-symmetric, but it's a real thing which is not LASIK, is used, for example, in this pointer.
yes.
Okay. Yes, up now?
Nonlinear loss is, so we didn't consider nonlinear loss. Of course, it will, in our discussion, complicate everything and give an additional source of loss, which has, in a PT-symmetric system, also to be compensated by additional gain. And I think this will be very challenging to get this also nonlinear.
Is it important or not important?
For of course, in an experiment, one can, for sufficiently long times, ignore it. So, this is so. Is this the question? Okay.
Oh, I see the laser people are. If you have a question, you should be lasing at him.
Maybe in the coffee break.
I just wanted to ask something, because something that you mentioned in the beginning. You refer to the to the parity of the wave function in the Gross-Pitevsky, but in order to have PT symmetry for the system.
Yeah.
Yeah, but couldn't you just look at the Hamiltonian, which gives you the Gross-Pitevsky equation, and make sure that it is itself PT symmetric?
So
some
okay.
properties of the
This always,
operator.
this linear.
No, and then Hamiltonian, Hamiltonian, which Gross-Pitevsky is Hamiltonian. No, you can derive it from a Hamiltonian.
Oh, okay.
Yeah.
So this, yes, of course, you can do this PT symmetric, but this also has this interaction part, which depends. Also, in this case, depends on how the particles are distributed, and of course, the linear system then will be PT symmetric, but okay, this might be an effect only of the mean field approximation that this comes into play here.
Okay. Any other question? If not, let's thank the speaker again. And,